we've been talking about Pascal's principle, and let me remind you, Pascal's principle says that if you have a fluid-filled chamber with two ports with different areas, area out and area in, the forces obey this relationship. And how did we arrive at Pascal's principle? Well, so far we did it in two different ways. So one way to arrive at it was treating the fluid-filled chamber like a machine, where the work you put into it is equal to the work you get out of it. That was way number one, that we derived Pascal's principle. There was a second way that we derived Pascal's principle, and this was by considering little cubes of fluid and how they transmit forces through a chamber full of fluid. So I imagined all these little cubes of fluid and how they transmit forces. This was method number two. So we imagined, forces acting on these, and then these exerting forces in other places. So that was the second way that we approached or derived Pascal's principle. And now I want to show the third way. I'm going to do this kind of briefly. I don't want to spend a lot of time on it, but this is by using the concept of the center of gravity. And as a reference, where Pascal talks about this is on page 185. So this is on page 185 of A Student's Guide to the Great Physics Texts. And here, let me see if I can find the specific reference. I guess I take it back. This is not on page 185. Let me erase that. Where is this located? This can be found on page 181. And if you look at the second full paragraph, Pascal says, here is another proof of Pascal's principle, which only geometers will be able to follow and which may be passed over by others. So consider this for the geometers among you who are interested in this kind of thing. This is his third explanation. So let me remind you what we mean by the center of gravity. So we've come across the concept of center of gravity before in this class. And so let's imagine that we have a lever. This is probably as good a way as any to introduce the concept of center of gravity. And we have two big masses sitting on this lever. And we can place a fulcrum right here in order to balance those. So you remember, if this one has a weight W1 and this one has a weight W2, I've drawn it bigger to indicate that this is a larger mass than this one, then in order for them to be in equilibrium, you cannot have the fulcrum right in the middle. You need to have the distance D1 bigger than the distance D2. That's to provide equilibrium. Where you have to put this in order to be in balance, well, that happens to be what we call the position of the center of gravity of this two-block system. So if our system consists of these two blocks, then the center of gravity is the location we would have to place the fulcrum in order for them to balance. If we want to, we can think of the center of gravity of a fluid-filled chamber as well. So what I'm going to do is I'm going to draw one of our fluid-filled chambers, and like Pascal, I'm going to draw two columns that are, as he says, soldered into the top. And what I'm going to do, I'm going to imagine that we have those two columns. I'm going to copy this, because I'm going to need this in a moment. Edit, copy it, and then I'm going to paste it. Let's paste a copy of that right here, and then let's paste it again. I might need 3 copies. Oh, I didn't mean to expand it. Let's move it over to here. Okay, and get rid of that. Okay. Now imagine we put fluid in this fluid-filled chamber. So I'm going to imagine that the fluid is the same height on both sides as it would be if these are two openings. And what we're going to do, let's just ignore this region right here and just concentrate on this region of fluid right here. Now, this region of fluid has a certain weight, and this region of fluid also has a certain weight. You can almost think of these two little regions of fluid as being two masses, like this. And you might imagine that because on the right-hand side, this one has more mass, the center of gravity of this these two blocks of fluid is going to lie closer to the right-hand column than to the left-hand column. Now here's the question. What if these were not level? So for example, if on the left-hand side the fluid level was lower than on the right-hand side. Let's imagine if this were the case. What do you think would happen to the center of gravity? Well, because we can think of this as being a mass and this as being a mass, what ends up happening is that the center of gravity is a bit higher. It's over on the right-hand side, and it's also a bit higher than it was before, because this mass is larger and it's up higher. So the center of gravity of the system is higher. And similarly, here's something else. What if the fluid level on the left-hand side was higher than the fluid level on the right-hand side? What happens then? Well, you can actually calculate where the center of gravity of this system would be. Again, we have the same amount of fluid in each of these three cases, but we're asking where the center of gravity is. And now you're going to find the center of gravity is also a little bit higher than it was in case 1, like this. So in case 1, I guess I could label this case 1, case 2, and case 3. As it ends up, let me remind you that there is fluid in each of these chambers like this. What ends up happening is you'll find that when the fluid level is equal on both sides, the center of gravity is lowest. And whenever the fluid level is adjusted so that it's higher on one side than the other, the center of gravity actually goes up. And so this is how Pascal explains why these fluid levels must be equal. If you look back on page 181, he says in the final paragraph, he says, "I lay down as a principle that a body never moves by its own weight without downward displacement of its center of gravity. Whence I prove that the two pistons are in equilibrium when their level is the same." Okay, so in other words, if you somehow were to push the fluid down on this side and raise it on this side, the center of gravity of that system goes up. And if you were to push down on this side and cause this side to go up, the center of gravity also goes up. So the situation wherein the center of gravity can be lowest is when they are equal. And so this system as a whole will try to act in such a way as to lower the position of its center of gravity. And the best way to do that, or the only way to do that, is for the fluid levels to be the same on both sides. So the system will attempt, so to speak, to adopt a configuration wherein the center of gravity is lowest. And to do this, so this is accomplished by equalizing the fluid level on both sides. I have not demonstrated this mathematically. One can demonstrate it mathematically if you want to. So for example, one could make a plot of the height of the center of gravity as a function of the height of the fluid on the left side. And this point right here is going to be when the height of the fluid on the left side is equal to the height of the fluid on the right side. And we would find, if we plotted this, let's use a different color, that the height of the center of gravity has a minimum when the height of the fluid on the left side is equal to the height of the fluid on the right side. Again, I haven't demonstrated this mathematically, but one could do this, but I am not going to spend the time right now going through that. I am just giving you a brief explanation of Pascal's third explanation of Pascal's principle in terms of the height of the center of gravity.